So hi everyone. Today I will show you how we build a generative space of expression of emotions for virtual agent using a psychological data-driven method. And so firstly, why? Why virtual agent need expression of emotion? Why do we need the generative space, and why we use a psychological data-driven method? It's very easy to understand why virtual agent need a expression of emotion. Firstly, the emotion can help them to increase their human likeness and their agency, and this can also help them to raise the empathy from the users. Why use for expression? Firstly, it's the common used signal for human to communicate with each other and transmit the emotion, and it's also one of the most powerful social signal to transmit to perceive the emotion from others. Specifically, because virtual agent always communicate with participants using voice, and when voice comes with the expression, it can actually increase the semantic understanding for the users. Then, why we use generative space? We all know that most of virtual agent use the categorical emotion, for example, specifically the basic six, for example, happy, sad, surprised, disgust, and etc. Here we use affective psychological dimension, violence and arousal. So you can see from the figure, it come from negative to positive and come from calm to energized. And the reason we use this two-dimensional space is because firstly, it can provide a full range of emotion. As you can see, there are a lot of different type of emotion, and it's also very sufficient. So we will show you later that use this way of modeling, we can provide a different kind of emotion category other than basic six. Why do we use a psychological data-driven method? Firstly, what is psychological data-driven method? It's also called psychophysics. So basically, we reverse engineer the sensation template from random stimuli of participants. In our case, we will get individual preference of expression from human participants in the perception task. In this way, we can get the template of individual users. So it's a personalized model. Also because it's directly come from the perception task, so it's psychological validated. Okay, so how do we do the modeling though? I will explain this in detail. Firstly, we will show the fixed expression animation like this one to participants. All of the fixed expression animation is randomized, and we will show thousands of this kind of trials with different dynamic features, and the participants will see all the trials and do effective judgment task. In here, they will judge the arousal level of the expression, get all of the trials for high arousal. We can get overlapping of feature in high arousal expression. Then we can know, okay, this is the feature for expression of high arousal. Specifically, how do we generate the random expression in the first place? We have a animation generation toolbox which use the fact. So basically, Ekman use this individual independent face muscle to code the expression into different action unions. I will just call it AU later. And we have 42 AU in total. We have, for each AU, we have the different temporal parameter in here: acceleration, peak amplitude, deceleration, and peak latency, etc., to control the dynamic feature of different action union, but keep the move set itself in the same. We will choose 1 to 4 randomly out of 42 action union in one trials, give each of them random dynamic parameter, and combine them together as individual trials. Participants will, each of the expression animation will be 1 quadriseconds. We recruit 40 participants to do 1,200 trials for each of the valence rating task and the arousal rating task. With this, we can then get the action union which are frequently chosen as each bin of the task. So we can know, okay, this action union will be connected with these effective states. Using the use this data-driven method. Firstly, we are not theory focused. We have no assumption of what the expression will look like. And then we can get the perception of individual participants. And also because all the features are quite strong, so we can make sure it's recognizable signal and feature for the expression. Rebeing 7 to 5 to provide enough trial of each being, we get the expression of the two-dimension valence and arousal from negative to positive, low and the high from left to right. The color shows the consistency across 40 participants. Now we have the expression of the two individual dimension, but we need to combine these two together so we can provide a full range of emotion in space, and it can provide specific emotion signal in specific context for the virtual agent to deal with different situations. To combine the two, we first need to make sure that the information transmitted from the two dimensions are not conflict. So firstly, we try to get the action union negatively associated with each being. So using the to find out, we find out the action unions are very little frequent in each being to show here. For example, the facial expression in each being negatively associated with the balance level. And then we need to find out the action union that we are specifically associated with two dimension. Let me explain, use an example here. So the non-string expression action unions will strongly associate with not only negative, but also high arousal. So we will not see this action union in positive part or low arousal part in our modeling. Okay, now we need to pairwise the five expression in advance and 5 expression with arousal, but to get a 5 times 5 valence and arousal space, but remove the conflict AU as I mentioned before, then now we have this 5 times 5 space for expression to transmit a full range of emotions. So we can see here the expression transmit information from low arousal and the negative from the left bottom to the energized happy face in the top right. So we can get the expression to transmit exactly what the psychological space intended to. But the question now is whether this can really cover all the tasks for virtual agent. For example, can they transmit any kind of emotion category? So let me test this. Firstly, we mapping the expression of basic 6 emotion onto this valence arousal space. Mathematically, we code each of the expression into a 42 times 1 binary vector in the the one in the middle panel. Then we correlate the vector itself. So in the vector, the 1 and 0 shows whether the action union is presenting in this expression model. Like the green frame shown here, for example, we correlate facial expression fair with the expression of low arousal and very positive together by correlate the vector between the two. After all the calculation, we can get a distribution of how similar of each emotion, expression of each emotion category and each cell of the valence arousal space. Here is all results of the similarity distribution. As you can see here, for example, happy or very high correlates with all positive cell and span all over the arousal part. To validate our distribution, we also plotted the semantic rating of the emotional words here. I use this blue circle and from another data set from another lab, and black line is the standard deviation of the emotion words rating. As we can see here, each of the emotion occupy a different region of this space based on the similarity of expression. For example, surprise is slightly positive, but in high arousal, and sad is basically low arousal and negative. Each of the emotion occupy totally different parts. So to formally test this, we cross-correlate the distribution pattern of the similarity. As you can see in the diagonal, almost all the emotion are different from each other except for the disgust and anger. They share quite a lot in the negative high arousal cell. Then we apply similar procedure to 19 complex emotions. For the brevity of the presentation, we will only show the correlation of the distribution pattern. But the key point is that how good the fixed expression similarity of the basic 6 emotion and complex emotion are similar to the semantic mapping of these words in the valence space. To test that, we scatter plot all the emotions based on, firstly, their location of expression similarity mapping. Here exactly is the cell with maximum correlation in the distribution pattern figure, and also their semantic location, which is the rating of emotion words from the semantic rating data sets. And here in this figure, red represents basic 6 emotion and blue represents complex emotion. Furthermore, we also regress the scatter points of these emotions, which show quite a high correlation. This means that the similarity of the fixed expression of category emotion and all space are sharing same region of the semantic meaning of these emotion words. Let me conclude. Using a psychological data-driven method, we provide a generative space of dynamic fixed expression for virtual agent to transmit a full range of emotions. We test our fixed expression model in 25 basic and complex emotion fixed expression. It enables the virtual agent to provide different variability of different emotion categories. And that's it. That's the end of my talk.